Hello and welcome to Toddcast number 62. We're going to continue on with aldehydes and ketones, which we started with Toddcast 61. And want to look at it in a little more depth and simultaneously try to put it into a simple package, more of an algorithm, a flow chart to figure out what's going on in carbonyl chemistry. And it starts by realizing that the carbonyl reactivity is rooted in resonance. So as we know, pi bonds can break and they can form. So if this one breaks, the electrons in the pi bond come up here, they're going to go to the more electronegative atom, which is oxygen. So one resonance structure will show a sigma bond with a negative charge on oxygen and a positive charge on carbon, but it lacks an octet, so this is a minor resonance contributor. This is still your major, but that still averages out on over time to have a partial negative on the oxygen and partial positive on carbon. Chemistry at its simplest form is figuring out where the negative is and where the positive is and making them react. So this negative can react with a positive somewhere else, or this positive can react with a negative somewhere else. And we're going to take advantage of that phenomenon. So because the carbon of the carbonyl group is partially positive, it is susceptible to nucleophilic attack, meaning something with a negative charge, i.e. a nucleophile, will want to come in. And when it does, that'd be a fifth bond to carbon, so the pi bond has to break, send electrons up to the O. So for a brief moment, there is a tetrahedral intermediate. The lifetime is open to debate. The ability to pick it up by spectroscopy is open to debate. And there are definitely some textbooks out there. And for some of you who are reviewing OChem for a standardized test, and this is something you're looking back on, your professor you had might have actually referred to it by something as a tetrahedral transition state or a tetrahedral structure and not mentioned, even gone into the controversy. But I still stick with tetrahedral intermediate because, to the best of my knowledge, it has a long enough lifetime that we can call it an intermediate. Okay, so here's what we have. If a nucleophile Nu comes in, so if I have some nucleophile with a lone pair of some sort come in, it can form a bond to carbon, which it has right there, and it breaks that pi bond, which is why there's a sigma bond, and it's now 1, 2, 1, 2, 3 lone pairs, and you end up with a full negative here and a full positive on the nucleophile. So the point being, this seems reasonably stable. If this kicks in, it can kick the nucleophile back out. It might be reversible, but it's not going to be able to kick out carbon-carbon bonds. So the alkyl groups are on there to stay. So that's going to become fairly key. Exactly what happens with that intermediate is going to dictate a lot of the chemistry. Okay, because it is a good electrophile, it's also potentially a good acid, a source of H+. So we have to consider its ability to act as an acid and its ability to act as an electrophile, which means the other compound is either going to act as a nucleophile or as a base. And so a lot of times it's easier to consider the other compound first. So the two questions. First question, is the other compound acting like a nucleophile and attacking the carbon, delta plus carbon, the electrophile? Or is the other compound a really strong base that comes in and removes a proton from that carbonyl compound? So we need to consider that as the first thought. So if it's a nucleophile, then it will just simply attack the delta plus carbon and push the bond up. So it's something we've definitely seen. That'll come up and that'll form your tetrahedral intermediate. Or if it's a base, this is something to get used to, but the alpha carbon, refer to this alpha because it's one away, ends up having a very slightly acidic proton. They have pKs anywhere from 17 to 20, depending on what the other functional groups are. But if the base comes in and takes it off, those electrons can go up here to form a pi bond and break that bond. So you end up with this species. Okay, this compound in itself is a great nucleophile, not because O wants to donate, but because it can donate in, and those electrons can be shared with something else. So you can end up replacing that H with some other electrophile, and we'll go into detail on exactly what that is. The second question, so the first question is, what is it reacting with? Is it an acid-base reaction, or is it a nucleophile-electrophile reaction? And then is there a leaving group? Because if there is a leaving group, then it's going to substitute. It's going to form a tetrahedral intermediate. That O minus is going to kick back in and kick out the leaving group, and you will have substituted the nucleophile for the leaving group. But if there is no leaving group, Then you end up adding the nucleophile to the carbon and a hydrogen to the O. And so you end up getting an OH group and then some new group attached. So you may just think about sodium borohydride or lithium hydride, AlH4. That's a negative. That's a case where, let me get rid of this new in N and just turn it into an H minus, which would put then, this compound would have those two R groups, and then it would have an H coming out that would eventually get protonated and turned into an alcohol. So it would be an addition because there's no leaving group here. So you've already seen this. You've already seen that like nucleophile, and then you end up protonating the OH and get an alcohol. So that was an addition reaction. You've also seen substitution, kicked out of Cl. So want to look at this a little more carefully. Want to look at it in context. It sounds simple, and it is if you've seen enough of these that it becomes really familiar. But early on, the chaos and the overload of information will make it so that it will not seem simple. So two questions, nucleophile or base? When you're dealing with carbons, your H is not terribly acidic. H's on carbons, pKs are not terribly low. You might be lucky if you have a pK as low as around 17 for an alpha, maybe a 26 for a terminal alkyne, but they are not very acidic, which means it's only if you have a strong enough base to take it off that this can happen. So amines, if you recall, are weak bases, so it's not going to be strong enough to deprotonate, so it's going to end up acting as a nucleophile. So first question, it is a nucleophile. So too weak to protonate CH, so it's got to be a nucleophile. Second question, is there a leaving group? Absolutely. Cl is a leaving group. Okay, so because it is not acid-base, it's going to be a nucleophile and it's going to attack. So it's either going to be addition or substitution, has a leaving group, so substitution of the carbonyl. So here's a sample of how that reaction works. Let me get rid of my circle. Nucleophile comes in, electrons kick up. So as mentioned, you get a tetrahedral intermediate where you have 1, 2, 3, 4 things attached. I'm going to arbitrarily put this one out in front, this one in the back. But reality is it could be the other way as well. Could attack top or bottom, end up with either intermediate enantiomer. Okay, when the O kicks back in, electrons from that O are going to kick back in, so there's a lone pair. And I should probably specify that there's 2 lone pairs to begin with. There's 3 in the intermediate and 2 in the end. It'll kick back in, kick out the Cl. So you substituted an amine for Cl. Eventually, you're going to deprotonate that amine, and Cl minus may be the compound do it depending on the solvent you're in. So it's going to fluctuate, but in all likelihood, it'll probably be another amine that comes and deprotonates this. Okay, so next on the agenda, let's look at the second reaction. CN is actually the conjugate base of a weak acid, but it's still weak itself. So you're talking about a pKa of 9.2-ish. So pKb of 4.5, that's still too weak to be a base. So it's going to be a nucleophile. And there is no leaving group this time, so it cannot be substitution, so it ends up being addition. So addition across the carbonyl, so it's going to attack in, kick this up. So once again, you have a tetrahedral intermediate. I am still going to draw the stereochem just to emphasize that it's there. This time, you cannot have the leaving group get kicked out because there is no leaving groups. So it's not going to kick in and kick out an alkyl or the CN you just put on. So you end up protonating it. Picks up mild acid, and in doing so, you get CN and an OH. And this is actually fairly, I don't want to say common, but it's definitely a known reaction. You can add 1 extra carbon to some aldehyde. So perfect example, well, this is a ketone to an aldehyde. So if you have an aldose, a sugar that's an aldehyde form, you can extend the chain length. You can synthesize a one carbon longer sugar. Okay, next on the agenda, nucleophile or base. So this is our borderline one. It's strong enough to be a base and deprotonate it, but it's also potentially a nucleophile. But in this case, we're going to have it act like a base. It's going to be strong enough to pull off that proton. Now, the reality is that the pK of the acid, conjugate acid, is 15.5. This one's around 17.5, let's say. They differ by 2. 10 to the 2 is 100. So it ends up, it only takes off 1 out of every 100, which doesn't sound very good, but that's all you need. If you can just take off enough so that there's 1% of the solution is a really good nucleophile, then that nucleophile, the one you're generating, is going to be a better nucleophile than this. So it's going to end up being a nucleophilic reaction. We'll show how in a second, but it's going to act like a base. There is no leaving group. So it's going to be an addition reaction. But this will be something that will come up down the road. It's going to be an aldol addition reaction. So we'll show that in time. But for now, you deprotonate the alpha carbon. It's going to deprotonate, and it forms a great nucleophile. And what can happen, these electrons can kick back in, that those pi electrons can come out. So if you have something like an Rx, fairly common thing that happens, you can actually extend your chain length to be R, CO, CH2, R prime. So let's say I have a so-called methyl ketone. So if this is 4 carbons, let's say this is 5 and 6. So let's say we have 2 hexanone. I can add an R group and it might be, let's say add ethyl, then it becomes 4 octanone. Or depending on how many carbons I add, I can increase the chain length of that ketone. So it's called alpha addition of whatever it might be, in this case an R group, to the alpha carbon. So you make a great nucleophile. So again, this acts like a base to convert the carbonyl. 1% of the carbonyl is a nucleophile. 99% is still in the ketone form, which means this great nucleophile is surrounded by a lot of the same compound. So it could attack itself, or it could attack this compound, which is a little more reactive. So we'll get into a lot of reactions based on this, but your job early on, be very systematic. Treat everything like an algorithm when you're dealing with carbonyls. First decide, is the other compound going to be a nucleophile or a base? And from there, make a decision if there's a leaving group or no leaving group, and you'll be able to solve questions fairly quickly. Okay, aldehyde and ketone addition. So I want to look at these just simple cases under acidic conditions and basic conditions, how it works. So a nucleophile under basic conditions will typically carry a negative charge. It'll be a very strong nucleophile, and as such, being negative, it can attack the carbonyl. So under basic conditions, you have negative charges. Nucleophile comes in, kicks that up, and you end up with an anionic intermediate. Can't kick back in and kick out the nucleophile, can't kick in and kick out the 2 R groups because they're stable. So it ends up picking up an H. So want to emphasize that under basic conditions, you would not have this compound. So tossed it in there in this way. This is a very typical mistake people make where you put a negative and a positive. Can't have that. So what you end up getting is this compound can only be water. So cannot have a protonated water and a base present. So same thing, you're going to have this O minus kick in. So let me let the computer do that drawing. So give me on that one. You're going to end up having that go over. And so you'll end up with that compound. But I want to emphasize the other compound coming off is OH minus. Okay, so far so good. So you cannot have that positive in the presence of a negative. So just want to put that out there. But under acidic conditions, you definitely can. So under acidic conditions, you do actually need an acid. I'm going to put this in HA, so catalytic acid, but it could just be H3O plus. It's going to pick up the H, generate an A minus. But this species is the key species involved. To get rid of the plus charge, those electrons can go up, and a nucleophile can come and attack. Again, I want to emphasize something. In the presence of an acidic condition, your nucleophile actually can't be a negative nucleophile. It would get protonated by the conditions. So I need to redo this, and instead of making N negative, it's N neutral. So I know I'm probably like just being just over the top anal about this stuff, but really want to emphasize a typical mistake was the one I made up here by making H3O plus. Typical mistake is one where I made the nucleophile negative. So under acidic conditions, you have positives and neutrals. Under basic conditions, you have negatives and neutrals. Negatives and neutrals. Okay. So, and again, bring it up because it is a very common mistake that is made all the time in mechanisms. And when you take a test, if you do that, you will lose points. So one last thing to make note of then, this nucleophile is positively charged. It can deprotonate and be worked up and turned into something neutral. But under acidic conditions, neutral and positive. So you should need to have a positive traverse through the pathway. Okay. Last but not least, want to mention there's lots of different nucleophiles we've dealt with. I want to look at altogether 5 categories, the ones with oxygen. You can have water or an alcohol attack, which we already have. We actually saw that in a couple of situations. We had attack carbonyl. We also had it attack an epoxide when we did alkene chemistry. And then we did protecting groups where we had a diol attack and formed that cyclic ketal. Hydrogen, we already did this with lithium aluminum hydride and sodium borohydride. Carbon, we've got alkyne nucleophiles, cyanonucleophiles, Grignard reagents. We're going to have something called the Vitti reagent. So I'll leave that for down the road. Nitrogen nucleophiles, we looked at amines. We have those, primary amines, secondary amines. And then sulfur. You can have sulfide attack, thiols attack. Oh no. This is not boding well. Hopefully you can still hear me while my computer hopefully plays catch up any minute. There we go. So this is one of those points where I apologize. I do first contact recording, just basically, I think there's something healthy about doing it that way. Number one, if there's a mistake, you learn from it. That can be beneficial. And then number two, it just gives it more of a natural flow. So I apologize for that pause there. Not sure what technology issue kicked in, but we're back in business. So you can have thiols, a dithiene. We'll look at all of these down the road. Now, the ones we've seen already, we have definitely added water to a carbonyl. We've added the RO. We did the actual mechanism for these. We did a protecting group. So all 3 of these you've already seen. So you're down. And the new ones you have to learn because you've already learned 3 of them. We've also already done sodium borohydride and lithium hydride. So you've learned these 2. We did the Grignard. We literally just did the cyano. And we literally just did an amine, although it didn't emphasize exactly the difference between primary and secondary yet. So I'm going to give that a check, but realize that we're going to have to revisit a little more depth. But you've already done 7, so you have 1, 2, 3, 4. Now you've done 7 to 8, so you have 4 to 5 to go. Okay, so covered a lot of general information. It is really imperative that when you start looking at carbonyl reactions early on, you break the process down into something you can repeat over and over and over. An algorithm beats a pool of memorized information. Is it a nucleophile base, the other compound? And number 2, is there a leading group? Okay, so we are done with yet another podcast. So hopefully it is going well. I will go ahead and call it a podcast at this point, and I will see you at the next recording.